Okay, and finally, for today's class, we're also going to be seeing a couple of examples using bagging and random forests. Remember that during the theory part of this class, we explained how bagging approaches, what they do is that they basically create different subsets by sampling with replacement from the original dataset, and they train different classifiers using each of these different data sets that we have created. Okay, and then again, the final label or the final value is basically a combination of all the values or the output labels from all the different classifiers. Okay, the main difference between bagging and random forests is that random forests don't use all the features. There's some optimization at the levels of features, the numbers of features that are used during the training. Okay, and random forests specifically focus on applying bagging to decision trees. So let's see a couple of examples of how can we, train bagging and random forests with a different data set. We are now going to be using the Boston data set. The Boston data set, it's basically one of those data sets that's part of a package that is embedded within R. So, we just need to load the library to be able to use it, the mass library, the mass package. But basically, this data set has the MED-V, the median value of owner-occupied homes that you see down here, right? So this is the median value, market value of a given home that's owned by someone. And then there's other different characteristics from the neighborhood in terms of socioeconomic characteristics, environmental characteristics, geographical characteristics, both categorical and numeric, that can be used to be able to predict what's the value of that home, right? So again, the objective here is to predict the median value of occupied homes based on these different features that we have as part of the trees. And we want to use decision that we have as part of the data set, and we want to use decision trees to do that, right? So how can we predict median household values based on different features using decision trees? Okay. But specifically, because we've already covered decision trees and boosting, we're going to be looking at bagging, so the bagging of decision trees, and at random forests. Okay, so at how we can, a very specific case of bagging decision trees, where the number of features that we use at every single node is a subset of the total features that we have. We're going to be working with these different libraries. Remember to install the packages if you haven't done so. And then the library mass, that package has one data set called Boston. So to use that package, you need to use the command attach. Okay, so we'll do all of that. And then we'll basically just create a training data set. So let's go for it. Let me move this to the side. Okay, so we're going to be loading this set of libraries: ISLR, mass, random forest. Now we're going to attach the Boston dataset. That's part of mass. That's fine, don't worry about those. And now we're going to create a training dataset. So as usual, we add a seed to add the random process. And what are we doing here? So in this case, because of the way random forest works, we're just going to create a list. We're going to divide the training testing dataset. It's going to be 50% training, 50% testing. Okay, and the only thing that we need to input into the random forest package is the number of rows that we want to use as training set. Okay, and so basically what this sample command is doing is, from all the rows that we have in the Boston data set, just take half of them. Okay, just take, the number of row from like half of the number of total rows that we have in the data set. Okay, so, we're saying sample from all of these rows in Boston, and basically take the number of numbers that you need to generate is half of that, right? So if you take a look at train, what train has is basically 50%, or if the Boston data, let's take a look at the Boston data set. So the Boston data set, as you can see here, has 506 entries. So what the train data has is just half of those. So it has 253, okay, different numbers. And those numbers represent randomly selected row numbers from this data frame, okay? That's exactly what this train command is doing. Now that we have created basically the training data set, what we do is that we are going to train a model using bagging, okay? Now, because we want to use bagging on decision trees, we use the RandomForests package. So the RandomForests package allows us to train random forests, and we can train random forests with different subsets of features, right? But if you train a random forest with all the features you have, that's exactly bagging a decision tree. It's not a random forest because we are using all features, but that's bagging applied to a decision tree, okay? So I have usually described random forest as a type of bagging, and that's the description, but now we are playing it differently with the RandomForests package, and we are saying, okay, let's apply bagging as running the random forest, but considering every single feature that we have in the data set, okay? So if we take a look at Boston, right, we have here, different features, right? Exactly, we have 13 different features, and then, this column, which is the median value that we are trying to predict. And so what we're saying in this command is run the random forest to predict the median value for a house using all of this data set, right? But only with the rows from the training data set, these 253 different rows. And then aim_try, what aim_try represents is the number of features that we want to use from the data frame. And we are saying use all 13 of them, okay? And importance true is because then we also want to explore the importance of the different features. And so in this case, we're just saying bagging, we're just explaining bagging as a type of random forest when all the features are used, okay? Okay, so let's create that model. We're gonna call it Bag Boston, and then we are gonna use the RandomForests package. We say that we wanna predict the median value, okay, and we wanna predict it with all the features that we have in the data set, okay? The data set is basically the Boston data frame that we have used. The subset that we use for training is the different rows that we have specified in the training variable. Now we're going to be using every single feature that we have in there, and then we're also putting the importance to be able to explore the importance of the different features. Remember when we talked about random forests, how we can figure out how important different features are. So if we do this, okay, we train this model, we can now write the name of the model that we have just trained, and we can basically see that, we are using 500 different trees, okay? And that you can also use sort of, the percentage of the variance that's explained, the number of variables tried at each split, which is 13, meaning that we're using all the variables, meaning that this is bagging on a decision tree. Okay, so this is just training our model, right? We are training a bagging decision tree. And now that the model is trained, we basically want to see how good this model is to predict, right? And so then we save the predictions that come out of from the predict command, and we are saying, okay, let's use the bagging decision tree that we have just trained, okay? And then the data that we are going to be testing, it's basically the data from the Boston data set, but removing all of the rows from the training, okay? So this is, consider all the rows in the Boston data frame, except for the rows that are in the train variable, okay? And then all of the columns as well, okay? Okay. So if we look at pred is basically just, the set of predictions that we have, okay, for the different variables for different 253 rows that we have, okay? These are the predictions, the median home values in the thousands of dollars. And how can we see how well our model is performing? Well, we can compute the difference between these predicted values and the actual values that we have in the median value column, okay? And that's exactly what that command is doing. So we're basically saying, okay, let's compute the difference between the value that we have predicted and whatever value we have in the Boston data frame, okay, in column 14. Okay, and what this is saying is, let's compute the difference between the value that you have predicted, okay, and the actual value that we have in the data set, okay, and we square that and compute the mean. So we are computing mean squared error, okay, and the mean squared error is 13.30. We can obviously also try to plot to understand, okay, so is 13 a lot, very little. We can also try to plot the predictions as opposed to the actual values, okay, and see how the two relate to each other. So we want to plot the predictions, and we also want to plot basically all the median values for the testing data set, okay, and you can see that it goes like something like this. So it's not that bad, right? So the values that we are predicting are kind of similar to the values that the data set has. Again, remember that these values, the MEDV values, are in the 20s that we have here, so predicted in the 20s all the way up to around the 50s, which is what we see here. So the predictions that we have are really pretty good. Okay, sounds good. So this is for bagging. However, we also want to try random forests. Again, remember that the difference between a random forest and bagging a decision tree is just on the number of variables that we consider at each node, what variables we explore to compute the information gain and decide what variables we should continue exploring as we go down the tree. And so the only trick that we need to do is that the number of features that we consider are not going to be all of them, but rather only a subset of them. And so what I'm proposing here is that, we train exactly using the same command, random forest, exactly using the same training data set, but we just say that we train with only 6 features. And those 6 features can, again, change at different nodes, right, as we explained in the theory. But we are only going to explore 6 different features and see if that actually improves the results, okay? Maybe using a bagging approach, where we create these different subsets, but when we train the decision trees, we limit the number of features we consider. Maybe we are, maybe controlling a little bit more for overfitting, and maybe in the end the results will be better. And so we do exactly that, okay? We train exactly the same model, but in this case we only consider 6 features at each split node, okay? And then we do exactly the same thing. We use that new model that we have trained, that random forest, to basically predict on the testing data, okay? And we again compute what's the difference between the values that our random forest is predicting with the actual values that we have in the data frame. And what happens in this case? In this case, the correlation, or the mean difference is 11.56, which is slightly smaller, right, than the 13 that we got before with the bagging approach. And so what this means is that by reducing the number of features that we consider at the node level, at each node, when we explore the information gain, we are basically improving the accuracy of the predictions by a little, okay? And so I encourage you to basically, do this second prediction as well. It's exactly the same process. The only thing that changes is the number of features in the random forest command. And I also encourage you to explore a little bit. So the template for the random forest is that it uses 500 trees, as you've seen in the different examples that I have explained. So I'm also going to encourage you to play with other variables in that package, to, for example, change the number of trees and see what happens and see how that might affect the accuracy of the prediction. Okay, and I will see you next week, where we will be covering support vector machines and neural networks.